Hello everyone, let's talk about a gasoline engine, how it works, and why do we call it a forced cycle. A gasoline engine is a type of internal combustion engine that uses a gasoline as its fuels. That's why we call it a gasoline engine, because gasoline is the main fuel that burns the engine to create power. The engine mixes gasoline with air and the spark plug lights the mixture. This tiny explosion pushes the piston down, and that movement eventually turns the wheels in a car or motorcycle. Now, why do we call it a four-stroke cycle? The word stroke means one full movement of the piston inside the cylinder, from top dead center to bottom dead center, and also from the bottom dead center to the top dead center. In this engine, the piston completes four different strokes to make power. These are the intake, compression, power, and the exhaust in a two revolution of a crankshaft. These four strokes happen again and again very quickly, making the engine run smoothly because the engine repeats this four strokes to produce power.
Let's talk about intake stroke. During this stage, the piston moves downwards creating a vacuum. It moves from the top dead center towards the bottom dead center. Because of this, it produces low pressure, which makes the intake valve open, and a mixture of air and gasoline vapor is sucked into the combustion chamber. Think of it like the engine taking a deep breath bore doing work. A proper and balanced air-fuel mixture is important because it affects how smooth and efficient the combustion will be later on. This mixture is usually controlled by the carburetor or fuel injectors, depending on the machine design.
Now let's have the compression stroke, the second phase of a four-stroke gasoline engine. This happens right after the intake stroke as the crankshaft rotates from 180 degrees to 360 degrees. Let's break down how the piston moves and what happens inside the engine.
At the beginning of the compression stroke, the piston is at its lowest point, which is the bottom dead center or BDC. As the crankshaft rotates, the connecting rod pushes the piston upward, compressing the air-fuel mixture trapped in the cylinder. This upward motion reduces the cylinder's volume, forcing the mixture to become more compact and raising both its pressure and temperature. During this phase, both the intake and exhaust valves are completely closed. The camshaft, which rotates at half the speed of the crankshaft, ensures the intake and exhaust cam lobes don't actuate the valves. Thanks to this valve timing, the cylinder becomes sealed, allowing for full compression without any loss of pressure. The exhaust valve remains closed throughout this entire stroke and only opens during the exhaust phase. As the piston moves closer to the top dead center, the volume inside the cylinder gets smaller, causing the pressure and temperature to rise dramatically. By the time the piston reaches TDC, the air-fuel mixture is compressed to a point where it reaches around 150 to 200 psi, and temperatures can climb into several hundred degrees Celsius range. The compression stroke also requires energy. As the piston is forced against the increasing resistance of the compressed air-fuel mixture, the flywheel plays an essential role. The flywheel stores kinetic energy from the engine's previous power strokes and releases it during the compression phase, keeping the engine rotating smoothly and preventing it from stalling. As the piston nears the very top of its travel, the air-fuel mixture is at its highest pressure and temperature. This sets up the perfect condition for ignition. Just before the piston reaches TDC, the spark plug fires, igniting the compressed mixture and setting the stage for the next phase, the power stroke.
And that's the compression stroke, where the pressure and temperature rise to create an ideal environment for combustion. This critical phase ensures that when the spark plug ignites the mixture, the engine generates power needed to drive your vehicle. It all starts here with the compression of the air-fuel mixture.
During the power stroke, the fuel-air mixture inside the cylinder has already been compressed. At this moment, the spark plug fires, creating a strong spark. This spark ignites a compressed mixture, causing to burn very fast and explode. The explosion creates high pressure inside this cylinder. Because of this pressure, the piston pushed downward with a great force. The piston moves down and it turns the crankshaft, which changes the piston up and down motion into rotating motion. This rotation is what eventually drives the wheels of the vehicle. During the power stroke, spark plug produces a spark that starts the explosion. Also, the piston is pushed down strongly. The crankshaft rotates because the piston is moving from up to the bottom. So also the valves, both intake and exhaust valves, stay closed to keep all the pressure inside the cylinder.
After the power stroke, where the air-fuel mixture is burned, the engine needs to remove the burnt gases from the cylinder, and this process is called the exhaust stroke. During this stroke, the exhaust valves open while the piston moves upward from the bottom dead center to the top dead center. As the piston rises, it pushes the exhaust gases out of the cylinder and into the exhaust system. In terms of crankshaft rotation, the exhaust stroke occurs from about 540 degrees to 720 degrees of the engine cycle. However, the exhaust valve actually opens a bit earlier, around 40 to 60 degrees before the bottom dead center, and closes a bit later for about 10 to 20 degrees after the top dead center. This valve timing helps ensure that all the burnt gases are completely expelled, improving engine efficiency and preparing the cylinder for the next intake stroke. In short, the exhaust stroke is like the engine's ways of exhaling, clearing out waste gases so it can breathe in a fresh air fuel mixture for the next cycle.
Firing order in gasoline engine and why it matters. Firing order is the specific sequence in which the spark plugs ignite the air-fuel mixture in the engine cylinders. This sequence is fundamental design parameter determined by the manufacturer to ensure the engine operates smoothly and efficiently. For example, for our 4-cylinder gasoline engine, the firing order is 1, 3, 4, 2. Correct firing order ensures smooth engine operation with minimal vibration, smooth power delivery, optimized fuel efficiency, and balanced mechanical stress. If the firing order is incorrect, the engine misfires and vibrates heavily. Power output drops significantly. Risk of backfire and damage to valves or catalytic converter, and always double check the firing order in a service manual during the maintenance or repairs.
Now, let's talk about energy and efficiency. When a spark plug ignites the air and gasoline mixture, it produces a large amount of chemical energy, which then expands the gases rapidly and pushes the piston down, creating mechanical work. Gasoline engines are typically designed to be light, quick revving, and ideal for everyday vehicles. But in terms of thermal efficiency, it is slower compared to diesel engines. This is because it operates at a lower compression ratio, which then causes it to lose more heat during the combustion process. Still, gasoline engines run smoother acceleration, higher RPM capabilities, and cleaner and quieter operation, which are all useful for cars and motorcycles.
Now, let's talk about something very important, the common problems in a gasoline engine. First, misfiring. Imagine this. The engine is supposed to run smoothly, but the air-fuel mixture doesn't ignite properly. This can happen because of worn spark plugs, weak ignition coils, or dirty injectors. When this occurs, the engine shakes, loses power, and runs unevenly. It's noticeable and it can get dangerous if ignored. Next, overheating. Engine needs a proper cooling system to function. If there's a low coolant, a clogged radiator, or a broken water pump, the engine can get extremely hot. And trust me, overheating can lead to serious damage, sometimes even permanent. Then, there's fuel delivery problems. If the fuel pump is weak or the injectors are clogged, the engine won't get enough fuel. This can cause hesitation, stalling, or struggling to accelerate. It's like trying to run a race without enough energy, it just won't work. Finally, carbon buildup. Over time, carbon can form inside the combustion chamber on the valves. This reduces airflow, lowers engine power, and makes the engine run rough. The good news, most of these issues are preventable. Regular maintenance, checking spark plugs, fuel systems, and the cooling system keeps the engine healthy and running smoothly.